Hey guys, welcome back to this GCSE chemistry revision course brought to you by revisedchemistry.uk. Today we're going to look at atomic history, atomic structure, isotopes, and electronic configuration diagrams. Scientists haven't always believed that the atom looks the way that we believe it does today. John Dalton originally proposed the idea that all matter was made of tiny spheres called atoms, and these atoms could not be divided into smaller pieces. Not long after, J.J. Thomson suggested the idea of an atom made of a ball of positive charge, and within that positive charge were randomly distributed negative charges, called electrons. Ernest Rutherford wanted to test J.J. Thomson's model. He devised an experiment to test whether J.J. Thomson's model was correct. If the plum pudding model was correct, then all the alpha particles would pass just straight through, none would be deflected. However, Ernest Rutherford's experiment showed that some particles were deflected back or off in different directions. Rutherford then came to three conclusions. The centre of the atom must be very small, and it must have a positive charge. Also, the majority of the atom is empty space, with the negative electrons orbiting around the outside. To finally get to the current atomic model that we believe today, we have to talk about Niels Bohr and James Chadwick. Niels Bohr did calculations to suggest that not only were the electrons orbiting around the outside of the atom, but they all were orbiting at specific energy levels. Today we call these energy levels shells. James Chadwick was involved in the discovery of the neutron, bringing our current model of the atom up to 3 subatomic particles: electrons, protons, and neutrons. On the periodic table, there is a list of every element that we have discovered. Next to each element's symbol, you can find 2 values. One is a mass number, and the other is an atomic number. The atomic number tells us how many protons there are inside an atom of that element. The mass number tells us the total number of protons and neutrons. So to work out the neutron value, we just subtract the proton value from the mass number. The number of electrons in an atom is equal to the number of protons in an atom. This is because protons have a positive 1 charge, while electrons have a negative 1 charge. There must be the same number of protons and electrons in an atom because atoms are overall neutral. Every atom of the same element has the same number of protons. The proton number defines the element. We can change the number of neutrons in an atom, and this makes isotopes. Or we can change the number of electrons in an atom, and this makes ions. We're going to look at each of those separately. You need to know the relative masses of all 3 subatomic particles. Protons and neutrons have a relative mass of 1, while electrons have a mass that is so small we just write negligible or very small. Almost every element on the periodic table has naturally occurring isotopes on our planet. Each isotope has a different number of neutrons, however the number of electrons and protons remains the same. We can use carbon as an example to look at its 3 most abundant isotopes: carbon-12, carbon-13, and carbon-14. Carbon-13 and carbon-14 both still have 6 protons, like carbon-12. However, carbon-13 has 1 more neutron, and carbon-14 has 2, bringing their total neutron numbers to 7 and 8 respectively. We can use isotopes' abundances and mass numbers to work out a relative atomic mass. The relative atomic mass of an element is the average mass of all its atoms compared to 1/12 the mass of a carbon-12 atom. We can calculate the relative atomic mass of an element using the equation shown. We're going to use chlorine as an example. You probably have seen this one before. There are 2 isotopes of chlorine, 35 and 37. Looking on the periodic table, we can see that the relative atomic mass of chlorine is 35.5. We know that the mass of a proton and a neutron are both 1, so we can't actually have a half mass in an atom. What we're looking at is the average of 35 and 37. We have to take their relative abundances into account when we do this calculation. 75% of all chlorine atoms are chlorine 35, and 25% are chlorine 37. If we put these numbers into our equation, we get something that looks a little bit like this. 35 times by 75 divided by 100 added to 25 times 37 divided by 100. What we've done there is we've times their masses by their abundances, divided by 100, and added all of those numbers together. This gives us our relative atomic mass of chlorine. Why not have a go at calculating the relative atomic mass for hydrogen? Pause the video now to wait for the answer. By now you should know that there are 3 subatomic particles in an atom: protons, neutrons, and electrons. Electrons orbit around the outside of the atom in shells. Those electrons aren't just in random shells, they're in specific shells, and we actually have to fill shells up before we can start a next shell. Starting with hydrogen and helium, there is only one shell of electrons. Hydrogen has 1 electron in that shell, and helium has 2. If we look at lithium in the periodic table, it starts a new row. This is because we can't put any more electrons in that first shell. We have to start a second one. And so for lithium, we put 2 electrons in the first shell and 1 in the next shell. Moving down to sodium, we notice that sodium is actually in the 3rd row. Sodium, like lithium, fills the first shell up to 2. We then fill the next shell for sodium up to 8 and put the last electron for sodium in the next shell. We must fill each shell up first before moving to the next shell. The first shell takes 2 electrons. The second shell can take up to 8 electrons. The third shell can also take up to 8 electrons. You only need to be able to draw the electron configuration diagrams for the first 20 elements. Why not have a go at drawing the electron configuration diagram for potassium? Pause the video now to wait for the answer.